back to that?
Yeah, why not? Let's give it a whirl. Might help some people if they're absent.
There he is.
There she is.
I actually recorded it.
What you gonna test?
Having a time to put it.
Huh?
You gonna test it?
She graded it already?
Yeah.
It means a 65. Sure, got a 77. Vera got a 70. Highest score, highest in class was 90.
What'd you get?
Got 82, which is fine because the curve. If I get that, it's 86, 87.
I'm scared.
When Shrey and Vera get low scores, I mean that's when you know something.
My sister's actually, and then like ignore. No, lately I've been like when I'm washing my face, I don't like pretend on it.
The only one who can say it is Shrey, so I don't know.
So anyway,
She said she won't say it. Tony, what'd you get?
I don't want to talk about it. I genuinely don't want to talk about it. What you got?
I don't know.
She said it, she said it.
No,
Here,
it's so bad.
Lower score. Whatever you got.
No, you haven't.
You get 38?
No, I was
Okay,
so
you're good.
low. Who got the 38?
I know, so we're good.
Was this unit 3?
Yeah.
Oh, she didn't grade my
All right, folks, full disclosure, that camera is recording the lesson up here. You won't be on the camera. If you don't want your voice to be recognized, if you ask a question, do what they do in the old movies. You know, put like a paper towel over and the phone and go. So anyway, it's a what?
Hey guys, it's Nicole.
No, right now I'm just recording it on disc and then I'll. So we'll go over homework first, so I'll let you ask your questions, and then I'm going to present today. I promise this time you're going to have time to work, because I'm going to present everything you need to know about ionic bonding today, and then give you the practice, the homework to work. So let's go ahead and take your homework questions first.
I don't want to talk about it.
For 5
In the video.
Yeah,
for 5 you're supposed to like grade the plus and minus.
right.
But like, for B it was like they're both the same.
So what does that tell you?
They're non-polar.
Essentially, so there is no plus or minus, right?
So you don't write anything.
No, if it's non-polar, there's no displacement of the electron cloud, and so there's no negative and positive energy. Any other questions? If you didn't find the electronegativity table on my PowerPoint slides, you know, my slides are always up on my website for your access. If you find it helpful, I can start linking them directly into the calendar, and that way they're closer. So maybe I'll start doing that. But for the most part, it had the table of electronegativities. If it didn't, you could just Google that and find it. Yeah?
What's the answer to number 7?
7? Why are some bonds ionic and some covalent? I don't think I asked for that one, but I can answer it.
Oh, you didn't ask for it?
No, it's okay, but the basic answer to that is some bonds are ionic because the properties of the atoms, in particular the electronegativity, when it's a big enough difference, the pulling power differential is so high that electrons move over. Once that happens, ions of opposite charge form and they come together to form the ionic bond. Covalent bonds don't get to that point because the atoms we're talking about have more similar electronegativities, so they feel about the same. So they end up having to share electrons, which is a different type of bonding mechanism. So that's why. Any other questions from the homework, or are we good to go?
Can we look at the last question, 1?
Didn't I just assign 4, 5, and 6?
Yeah.
There's 1, 4, 5, and 6.
It's problem set 1. I think you saw that one.
Oh.
Which is fine. Again, I can still answer it if you ask about it. What is meant by a chemical bond? In general, what is meant by a chemical bond is the electrostatic forces of attraction that allow atoms to join together and form bonds, or it's bonds, sorry, and form structures like molecules and whatnot. What do atoms form bonds? Why do atoms form bonds with each other? General answer: to lower the energy of the system, which makes it a more stable system. So bond formation is generally to make the system more stable, like the release of energy. And then why do some elements exist as molecules in nature instead of as free atoms? Well, if you remember, that reminds us of the Hanfickel bride. The essence of this is, picture 2 hydrogen atoms in space floating around. There's an energy associated with that system. Then picture them joined together in a covalent bond. There's a different energy associated with that system. This is lower in energy than this arrangement, which is why when there's hydrogen atoms floating around each other, they end up pairing up like this to form a more stable structure. Everything is based basically on the move towards stability when it comes to bonding. And yeah, I think that was all. Is that good? Anything else? All right. Then let's zoom into the ionic bond. We went through that. We went through that. Let's talk about what this is saying here. So now that we have kind of the sense of dot structures, we can start to kind of predict even another way what type of chemical formula we're going to get when we form ions. So we've learned in the past that if we look at the charges, we can combine them to get to zero net charge. So like if I gave you this ion and say this ion, wouldn't you know what the formula should be? What would it be? Rishi, what would it be?
2F and then C.
Yeah, remember the positives first, right? So again, that's by the condition that the charges have to add up to zero. It has to balance. Now watch how we could have figured this out with dot structures, because calcium starts with 2 dots in its valence shell, whereas fluorine starts out with 7. So again, kind of just to show the usefulness of these diagrams in this context, you can see that fluorine is 1 short of filling its octet. Remember the octet rule yesterday? We said this pattern of nature is that we tend to fill up that outer shell to get to 8. So fluorine's 1 short, calcium has some to give. Since it's the metal, metals lose, non-metals gain. That would have the effect of making this calcium +1 and fluorine -1. Now, having done that, fluorine is now obeying the octet rule and is finished. But calcium still has 1 electron left over kind of in its outer shell, and if it would lose that, it would have a filled shell behind. So there's 1 more electron it has to get rid of, but there's not a, well, oh, I know. What if there was another fluorine? Couldn't we do it again? And that would make this -1, and this being gone would make it +2. And now we're back to kind of where we started. But here, when we learned this in Unit 2, I asked you to just memorize charges and make them add to 0. Now we're starting to see how the electron movements lead to this. And that the balancing really comes down to getting the electrons to kind of obey the octet rule. So in the end, we can see we get to the same formula. That's all that I wanted to kind of add to that piece. But here is where I'm going to teach you something you don't need to know for the exams. But I think without it, it's a really kind of empty understanding of the bond and why it happens. So I'm going to go through a little thing called a Bohr-Haber cycle, which shows us the energetics of the ionic bond forming. And that brings into something called lattice energy, which we're going to be able to predict comparatively. And then from that, compare like things like melting or boiling points of substances just based on the strength of their bonds. So let's get into that process. I'm going to start at the end here, and I'm going to tell you a question. Here's the question that I'm going to answer with you right now. What drives ionic bond formation? That's the question that you should be able to answer in relatively reasonable detail after this lesson. So let's start, like I said, at the end. I want to put up an image. I want to see if we can interpret it. This is called a Bohr-Haber cycle. It's just an energy diagram. Here's how it works. If you go up the graph, energy is increasing. You're absorbing energy, and you're becoming less stable as a system. When you're going down the graph, you're going down in energy, and you're releasing energy to the environment and becoming more stable. Try to see if you can figure out what all these lines mean. Let's brainstorm this. So I'm afraid you're going to have to actually speak up, because I'm not going to say any more until I hear somebody say something about it. What does this have to do with ionic bonding and why they form in the first place? Yeah,
Because one of them is attracting and the other is repelling.
good start, but there's a lot more to it than that. Where do you think this diagram starts?
At the bottom.
Almost right, not quite. The bottom is actually where it ends. In other words, after the reaction of forming the bonds is over, this is where we end up. What else do you see? What are all these little equations? Do they mean anything?
Probably.
They do, that's rhetorical. I'm trying to get you to look at it. What do they mean? Like, what is this first equation saying is happening?
It's converting to grams.
You mean gas?
Oh, yes, yeah.
There's a name for that process. Does anybody know what it's called when you turn a solid directly into a gas without passing through liquid?
About the reflate.
No? Yeah,
Sublimation?
that's it. What you see here is a process known as sublimation, okay? In other words, if you think about it, let me grab the model because you have to kind of see what I'm going for here. If I want to show sodium metal reacting with the element chlorine in the gas state to form sodium chloride, this structure, I have to take the sodium, and remember, if it's solid sodium, it's going to basically be a metallic solid with a bunch of sodium atoms all connected. But if all the sodium atoms are connected, how am I going to build this? Where there's chlorine, sodium, chlorine, sodium. So I have to take this apart before I can build it, right? These have to be separated. That's what this is saying. This is saying I took solid sodium metal, which has sodium atoms stuck together, and I'm pulling them apart. Why does that put me higher in energy? What am I doing if I take things that are stuck and separate them? Am I making bonds or am I breaking bonds? I'm breaking. Yesterday we said, anytime I break a bond, it costs energy. In this case, for the element sodium to be converted from solid to gas, 1 mole's worth costs this much energy. So right now, starting from the elements in their normal state and starting to build sodium chloride is not a good investment. So far it's costing us energy. We're becoming less stable. What do you think this is describing here? Just look at the equation. Right? You gotta be able to read this language that we call chemistry. What is it saying? Chlorine starts as Cl2 and then goes to Cl. What does that suggest is happening? Yeah?
Half a mole of chlorine, or
Molecules, yeah.
breaks up into 1 mole of just chlorine.
Yeah, in other words, we're taking these diatomic molecules and we're breaking this bond and separating it into just chlorine atoms. There's a name for this process. It's called bond dissociation. Again, why does that have to happen if I'm going to build this crystal? Because if I have a bunch of little diatomic molecules, I'll shade them different colors. Before I can build this structure, I have to separate this into individual atoms so I can interweave them with the sodium atoms. See, I'm showing you how we have to take things apart before we can build the new thing, and the energy changes that happen as a result. What is this? This you should know the name of. What is this describing? Sodium becomes sodium ion and an electron. Rishi?
Ionization.
This is it. This is the first ionization energy of sodium. So this shows ionization. I'll just call it the process. Now, up to this point, look at what has happened. We have taken the sodium metal and broken it into separate ions, or atoms. We have taken the chlorine molecules and broken them into separate atoms. Cost. Now we're ripping the electrons off of the sodium atoms to make them sodium ions. Whoa, huge cost. This process is not looking good. Forming these ionic bonds is very costly, it looks like. I just have to keep paying all this energy and to get even in the right place to get it to work. But then there's a breath of relief. What's happening over on this side? What do we call this process where an atom gains an electron and releases energy? What did we call this in the last chapter? Yeah. Which one?
Reduction.
Oh, that's true, but not in this context. You're right. The energetics of it is called something else. It was one of the trends we learned. How quickly we forget. Isn't this the electron affinity? That's what the electron affinity looks like. So this is the term that tells me how much energy is going to be given out based on absorbing an electron. Now I'm going to write something on the side for a moment. Let's review the octet rule in this context. Sodium is usually 1s2, 2s2, 2p6, 3s1. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. But look at what we just formed. We formed sodium ion, +1. So we lost this electron. We formed chloride ion, -1. Oops. So now we're here. Look at the valence shells. What do you notice is coincident with the formation of the ions? What happened to the electron clouds in both cases? Yeah, they obeyed the octet rule. They ended up with a filled octet. And now for the pièce de résistance, which is French for something. Given the facts that we've seen today, and I can also represent what you're seeing here with the dot structure, right? But given what you see on the board, I made a claim yesterday. I said some books get it wrong and they say, oh, the atoms want to have a filled octet and that's why they gain and lose electrons to form. Look at the board. Look at where we stopped. We stopped here so far. By this point, we have done everything we needed to get all the atoms filled octets. But look at where we started. And look at where we are now. Are we more stable than we began or less stable than we began? How do I know how to answer that? What do you think? Are we more stable than we started by that position, or are we less stable? Look at the energy, that's all I gotta look at. Are we higher than we started or lower? We're higher, that's less stable. If this were a business, you invested a bunch of money, made a little, back, but you're still in the hole. You haven't made a profit yet, you get what I'm saying? Because we started at line 1, at baseline. We did all those moves to get to that peak. That's all the energy investment. So far, we've only been paid back a little bit in line 4. Right now, it's a losing proposition. Just to get the octet rule satisfied does not drive this. In fact, it looks like we're going the wrong way. So where's the payoff? Why does this happen if all of this is true? Because what have we not accounted for yet? You notice I didn't look at one of the arrows? Which one could it be? Edison, what do you think this line is describing? Yeah, there's a word for that. What's this chapter about? Forming what?
Atomic. Ionic.
Bonds.
That was atomic bomb.
Well, it's ionic, but it's okay. I just wanted you to say, this is where the ions come together and form ionic bonds. So what you're seeing here is the process of ionic bond formation. There's a special name for this piece. This is the driving force of the whole process. This number, the energy released when you form a mole of the crystals from its ions, is called the lattice energy. A lattice is just a fancy word for a 3D structure like a crystal. Its formation from the ions is where you get the big payout. It's the biggest energy change in the whole process, and that's what I'm trying to tell you. This is what drives the bond formation. Because in the end, we ended lower than we started. This is energy released overall, right here. And you'll notice that when sodium chloride forms, particularly 1 mole, from its elements, it releases overall about 411 kilojoules per mole. It's very exothermic. You want to see what that looks like? I can't do it live. I found a video because I would have to use chlorine gas, and there's a small problem with chlorine gas. It's a deadly poison. So like, if I had it in the room and something went wrong, well, I'd probably die first. I'd be closest. Then you'd all be horrified, and as you stared at my death in horror, you'd all start slowly dying.
What if I held my
Remember, Graham's law of diffusion. What?
What if I held my breath?
Probably work, or you could just leave. Walk out the door, you'd probably live. Somebody drag me out and get me fresh air, would you? Thank you. Okay, anyway, but they don't allow me to have it, I don't think, so I don't. But I found a nice video that shows this process, I think, very cleanly. So let's take a look at it together. Voila.
Until it melts, just to burn.
So
Then it is immersed
that
into the
green gas is
yellow-green
chlorine.
chlorine gas.
That's sodium metal in the
The
little
sodium
spoon.
begins to burn in chlorine with an intense yellow flame.
Remember the flame test? Sodium makes a yellow color.
It produces a white smoke of sodium chloride. We are observing the exothermic reaction of sodium metal with chlorine gas, producing the white solid sodium chloride. Afterwards, the glass spoon contains only white solid sodium chloride.
So that's basically what it would look like. I mean, I know that wasn't that exciting. There was a better one, where they actually show molecular pictures.
Heat immersed into the yellow-green chlorine with an intense. We are being metal with chlorine.
I thought I had the better one. That's fine. It's just to show you what it looks like when it reacts, that's all. Anyway, so bottom line, what drives the formation of sodium chloride is the energy released, the lattice energy, when the bonds form. Cool? Now watch this. I went out of my way here a little bit, and I'm going to show you how the octet rule fits in with this. Why is the octet rule a thing then if it's not the reason? So I decided to try to build some fake crystals here and do the energetics. You don't have to look at all my things, but basically I did the Born-Haber cycle for magnesium oxide under 3 different conditions. One, where the magnesium and oxygen only had plus and minus 1 charge respectively. And you can see that the net result is a positive energy change, so that's not going to be very stabilizing. That's why it doesn't only lose 1 and gain 1. If you go to where the normal values are, when you use the +2 and -2 versions of these ions, you get a pretty reasonable output of energy. They say, oh good, more is better, let's go to higher charge. If you were to try to do it with a +3 and a -3 ion of magnesium and oxygen, look at the ridiculous amount of energy cost. This is completely unstable. So the octet rule happens because it tends to form the sweet spot. Maximum attraction for minimum input, relatively speaking. Look at why this killed us. It was that 3rd electron coming off of magnesium which we know is in the earlier shell, the deeper shell, in the core, that's what really put us over the top. So that's why magnesium stops after it loses 2, because it can now form a good bond that gives off energy, and it doesn't have to pay ridiculous amounts to get rid of the 3rd electron, which wouldn't pay it back enough to be worthwhile. It's just business, my friends. Rishi, you're a Deca, aren't you a businessman?
Yeah.
You get what I'm saying? If these are your choices, invest this and make that, but this is a loss, that's not good. But if you go through this series of investments, you get a nice payout, right? And then your business model says, well, let's try this way. Holy crap, that costs way too much, we don't get it back. Don't you take the best deal?
Yeah.
That's all I'm saying. You're going to maximize your profit. Here, the maximization of profit is the release of energy. Done. Okay. Now, how do we apply this? Do you have to do these little drawings? No. I wanted to give you a logical connection between the atomic properties and why they form a bond. Now that we have that, we can make some general conclusions in comparing how strong those bonds are. But first, I have to show you this. It's one of the greatest PowerPoints ever created. It's not mine, I stole it. Not gonna lie. But this has some of the best special effects you'll ever see in a PowerPoint. Are you ready for this? We shall now see live action drama of a Born-Haber cycle of sodium chloride formation. First, this is the net reaction. Sodium in the solid state plus half a mole of chlorine gas produces 1 mole of sodium chloride solid. We begin. I'm going the wrong way. Ready? Remember we said sublimation? The sodium has to come apart first. Watch this. No, 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 no. Want to see it again? Watch it. No, 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 no. I'm doing the sound effects. No, 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 no. Why did that cost energy to do? Hey. Good! Because we're breaking bonds. So that cost us. I know. Now the system has changed from solid sodium to gas sodium. Next move. No, no, no. No, 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 no. Oh, bond associate. No, 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 no. Bond association. We're breaking the molecules into atoms. Why does that cost energy? Same reason. We're breaking the bonds. Now where do we go from that? Oh, that's just my favorite one. Ready? No, 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 no. The electron is being shot out. Oh my God. I just. Let's go back. I want to see it again. Look, the electron cloud's bigger when it's neutral. And then his energy comes in and ionization. Bye, electron. Bye. How much does that cost? Well, it costs quite a bit. Now we have sodium ions in the gas state and chlorine atoms in the gas state, but that electron didn't just go nowhere, Elizabeth. Oh no! That electron ended up, guess where? Oh, I'm going the wrong way again. When I'm looking sideways, I get confused if I'm... Okay, watch this now. This is the best part. Ready? Oh, I did it already. Hey, where'd the electron? Ah, the animation got broke. It usually shows the electron falling in. Ah. Oh, there it is. See that? Whee! Ionization? No. Electron affinity? Yes. Electron falls in. Bang! Electron cloud grows because of repulsion. No, 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 no. But this time, ladies and gentlemen, we get some payback. Still, by the time we've reached the ions in their full octets, we're still behind. But then, no, 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 the reaction! Bam! The crystals and the release of the net energy of the reaction. So the payoff must have come from the formation of the crystal lattice from the ions. And there's your ionic bond formation that drove the process and more than paid for all the changes we had to go through. The octet rule is just a coincidence of nature that works to make the prediction. It does not drive. Energy changes drive bond formation, and that's it. But what we notice is this pattern that we tend to end up with filled octets as the atoms are bonding. And that's the moral of the story. Okay, near. Back to this. Aha! Ha, ha, ha. Remember this guy? I generalized it to Q for charge. It's Coulomb's law again. It's actually Coulomb's law twice. If you're in calculus now, you probably would know that if I told you this was basically the derivative of that for related, but they're both part of Coulomb's law. This one shows it as force, that one is energy. Simple. Listen to the simplicity of what I'm going to tell you. Just like before, the higher the charge of the ions, the stronger the ionic bond, because there will be more attractive force. Higher charges, and generally our charges are limited to plus or minus 3. So what I'm telling you is +1 to -1 attraction is much weaker than +2 attracting -2, or +3 attracting -3, and so on and so forth. The other factor is the size, meaning the radius of the ions themselves. The smaller the atoms are, the closer their centers may approach. And the closer they get, remember how distance affects, sorry, I know in physics they use R instead of D, it's the same. It's just distance. But the closer they get, the stronger the attractive forces will be. Make a note in your notes. This is extremely important to apply this. This is what you look at first. This is what determines the strength of the bond and the release of the lattice energy. But if it's a tie, then you look at the size of the ions. So always argue first from the charges. Then, if it's a tie, meaning you have the same charges in both molecules or formulas, then you look at the size to differentiate who's the winner. This will be clear once I show you a couple examples. Take a look at the lattice energies indicated for each of these ionic substances. Everybody in this group is pretty low, but they're not equal. These guys are all bigger than these guys. These guys are all bigger than those guys, and this guy's like, woo! How'd you explain that? How'd you explain this relationship? Remember, the lattice energy is a release of energy from the formation of the ionic bonds, and thus is a measure of the strength of those bonds. This bonding here is the strongest in this group. How do we explain this? Does anyone have a theory based on what I just told you? Sorry, you look like you know. Tell me at least, why is this one so much bigger than everybody else? What do you think is going on there?
Because nitrogen has a -3 charge.
Excellent! And what does that mean the scandium must have here?
A +3.
Those are very large amounts of charge. So there's a huge strong force pulling them together. So then why is lithium fluoride so much less than that one? What are the charges here?
+1, -1.
Good. Do you see how the charge effect has such a large difference in the strength of the bond? But wait a minute, aren't all the ones in this column +1, -1? They're all +1, -1, right? So the charges aren't really differentiating them. If only there was some secondary factor I could look at. You know? Good! I'm going to draw a picture for these first three, and I hope this makes my point. Then I'll tell you about my fat Uncle Charlie. So all the lithium ions are the same size, right? So these are all the lithium ions, +1. Fluorine is very small by the periodic trend, And since chlorine has more shells, it's bigger. And since iodine has more shells, it's even bigger. What I'm looking at is this internuclear distance. What's happening to the distance between the nuclei as I go down this list? What are the negative ions doing? They're getting. Yes, thank you. That increases the separation. This has a weakening effect on the bond. My fat Uncle Charlie, here's what he has to do with this. So Thanksgiving's coming up. Fat Uncle Charlie's coming over. He married a really skinny Aunt Martha. When Aunt Martha comes to hug me, she gets over there, pulls me in tight, and wraps her arms around me. I can get my arms around her like 2 times. She's thin as a rail. We get really close. Then I go to hug fat Uncle Charlie. It's like 450 pounds. Uncle Charlie! Trying to hug him. See where I'm at? I can't get as close to Uncle Charlie to get a tight hug because he's bigger. Aunt Martha's really little, so I can really get in there and hug her tight. Please tell me that connected to this in your mind somehow. Please tell me you get what I was trying to do there. I don't have an Aunt Martha. I don't have an Uncle Charlie. I made the whole thing. I made the whole thing up. Did it help at all? Did a little, right? Now we can apply the bond strength to the properties. Watch this. This is amazing. The power you're about to gain in your brain. Here is a series of closely related ionic compounds. They all have sodium and one of the halogens. You can see the interionic distance, which is basically how far apart the atoms are, nucleus to nucleus. You can see the melting point trend, and you can see the lattice energy trend. What conclusions can we draw here? Why is sodium fluoride such a higher melting point than sodium iodide? What do I have to do to melt a crystal? See this? See how this is a solid? Everything's locked up. To melt it, what do I have to do? What do I got to do to the bonds to melt it? I got to at least loosen them, right? I got to do work against them. They're not going to break fully. It's still a liquid. But I got to disrupt them. I got to provide enough energy to disrupt them. So why do you think sodium fluoride melts at a higher temperature? Start working with your brain backwards. What must be true of the bonds in sodium fluoride versus sodium iodide? Whose bonds are stronger? That one or that one? Who's got the stronger ionic bonds? Tell me.
The first one,
Why? How do you know this?
because it has a higher melting point.
Which means it takes more energy to disrupt. So it's stronger. You're right. Now let's look at the theory that could have predicted this.
Sodium and sodium both have +1 charge. Fluorine and iodine both have -1 charge. The charges are non-differentiating. The charges are not the key factor here. We must look at radius. Fluorine is smaller, iodine is bigger. Bigger, Charlie. Can't get as close. Weaker bond, lower melting point. That's it, it's so simple. What did I just say? Read that back to me. That's all you got was Charlie? I know this makes sense. I just don't know if all the words are going into your ear through your brain. Or if you're tired and they're like kind of in and out and you just hear, and then you hear, your name, you go like, what did you say? What was the question? Is that what it's like? Luckily, this is all on video. Yes? What's on?
So is it like, if it's a bigger distance, it has less energy, so it can't break them apart?
It requires less energy to break them apart. Because when they're larger, they're farther apart.
So like it used to.
Yeah, because if they can't get close enough, the bond isn't as strong. Because remember, Coulomb's law tells us charged particles, the force increases as they come closer. And that's the size is kind of what's preventing them from getting closer.
Yeah.
But remember, that's a secondary effect. Let me ask you to pick another prediction. This time I'm not giving you any data, just the formulas. I will give you 2 ionic compounds.
This one and this one. Which one has the higher melting point according to our theory? Which one should have the higher melting point?
For those playing along at home, what would you look at first to check for the higher melting point if we're looking at ionic compounds? What would you look at first? What would you assign to that?
Charges.
Charges! Charge of magnesium ion. Paula.
+2.
Chloride.
-1.
Calcium.
+2.
Oxygen.
-2.
Right. Who have stronger bond?
Bottom one.
Why?
Higher charge.
That's it. Yeah, but this has 2 of it. No, it doesn't matter. It's the size of the individual charges because that's what's interacting. You know the easy way to tell? Just multiply the 2 charge numbers and take the absolute value. The bigger number wins. 4 is bigger than 2 when you multiply. Because isn't this how Coulomb's law is? Just the charges are multiplied? It's the easiest way to tell. Do I have to look at the size of the ions this time? No. Charge wins. Justin!
Yeah.
Oh, sorry. Do you have your phone?
Yeah.
You take it out. Can you look up the melting points of those 2 substances for us very quickly in Celsius? And let's see if we predicted correctly. It'd be funny if we did.
Wi-Fi is so annoying.
Just put melting point MgCl2 and holler it out.
Let's 714 degrees Celsius.
Thank you. What about calcium oxide? But it's higher, but it's higher, but it's higher. I didn't even check. Tell the truth.
(2,613 degrees Celsius).
Like that? Why is it so much higher? Because what's bigger?
Charge.
And what makes it stronger then? What's stronger?
The bond.
Microjoule. Yeah, that's right. That's impressive. Right on the bell. You can now start working on the problems because now is where you're going to actually firm up if you've learned anything, or you'll firm up if you have any questions that I can address while you're here in front of me and I'm here to go, ooh, 4, 7, 8, 9, 10, it's all about ionic bonds and lattice energy. You should have no problem finishing it before you leave today, which is why, 2 reasons why. A, I'm giving you this time to do it specifically because I don't think your brain could take another topic right now. Am I right?
Yes.
B, you just sat and listened for a while, sporadically contributed answers to my questions, so you don't know if you know any of this yet. You have to work through it. These are the reasons. And reason B, this way I don't give you homework and you have more free time to spend with your pets. Oh, yeah. All right, video ends here. We will not record the doing of the homework. Thank you. Hope you've enjoyed the show.